first going to be looking at identifying some numbers here. So let's recall what numbers we have looked at so far. So we've got the integers, which is a subset of the rational numbers, which is a subset of, oh wait, forgot one. The natural numbers, the subset of the integers, which is a subset of the rational numbers, which is a subset of the reals. And then we've got the irrationals, which are also a subset of the reals. So how are we going to identify any one of these? Well, if a number is in decimal form like this, then if it ends, we know that this is a rational number. So at the very least, this thing is in Q. So 1.001 is in Q, and it's in R. This little E thing means in. Okay, it's in both of these. And if we get one right, we get everything to the right, just like Russian nesting dolls. Okay, we have 0.333 repeating. Well, if it's a repeating decimal, then it's also a rational number. So this is going to be in the rationals, and it's going to be in the reals as a consequence of that. What about negative pi? Well, negative pi isn't a natural number, it's not an integer, and it's not irrational because it's a very famous irrational. And the negative of an irrational number should still be an irrational number. Just because it's negative doesn't mean we can write it as a rational number now. So pi is in the, or sorry, negative pi is in the irrationals, and it is in R. What about negative 11? Negative 11 is not one of our natural numbers because our natural numbers are all positive, but it is an integer, which means it's a rational number and a real number. So negative 11 is in the integers, the rationals, and the reals. And 11, well, that's just one of our ordinary counting numbers. So yes, it's a natural number. It's in the integers, it's in the rationals, it's in the reals. 13 over 15. Whenever we have a fraction, we just want to double check and see if these are both whole numbers. Can we make it into an integer? No, it doesn't look like it. So this is just a rational number and it's a real. Square root of 16. Okay, square roots can definitely be irrational, but be careful. 16 is a perfect square, right? 16 is equal to 4 squared. So the square root of 16 is equal to the square root of 4 squared, which is going to cancel with the square root, so that's just 4. Well, 4 is a counting number. So square root 16 is in the naturals, the integers, the rationals, and the reals. 3.14, that's the start of the decimal approximation for pi. So I think this is trying to trick us up and say, well, this is irrational. But look, the decimal ends for sure, 3.14. If the decimal ends, then it's a rational number. Okay, so 3.14, definitely not an integer, but it is in the rationals and it is in the reals. And then finally, 15 over 3. So with fractions, we want to check if it's an integer. Well, 15 is equal to 5 times 3, so this is just 5. 5 is a natural number, so it turns out that 15 over 3 just 5. That's going to be a natural number, an integer, a rational, and a real. Okay, that was warm up. Let's do some little fraction stuff here. So if we've got 2 divided by 2 over 3 minus 2 over 3 divided by 2, well, we want to use our fraction rules. So if we have a fraction over a fraction, then we can just multiply and flip, right? Because if we have a b over c d, we can multiply these two, and then we can multiply these two, because this just becomes a over b times d over c. You flip them. So then it becomes AD, right? AD over BC. Easy. Okay. So 2, that's just 2 over 1, right? So we're going to have 2 over 1 divided by 2 over 3 minus 2 over 3 divided by 2 over 1. And why am I writing it like this? So I can just use this property right here, right? So I'm going to multiply 3 and 2 and 1 and 2. So on the top, I'm going to get 2 times 3. On the bottom, I'm going to get 1 times 2, right? These 2 and these 2 minus these 2 and these 2, right? So 2 times 1 over 3 times 2. Then we're going to get, well, this is just going to become 6. This is 2 minus, oh, well, 2's cancel, and this is minus 1/3. But 6 over 2, that's just 3 minus 1/3. And 1/3 away from 3. Okay. Yeah. Annie, are you talking about 29A, the one I'm working on right now? Sorry. Minus 1/3. And then I think the easiest way to handle this is to just treat this as a mixed number. So this is 2 and 2/3. If we really want to write that as an improper fraction, 2 times 3 is 6. So 6 plus 2 over 3 is 8 over 3. Okay. We'll be doing quite a bit of rational expression stuff today. So even though this is from the first section, I did pull out the fraction stuff. So we're going to do a lot of this. We're looking for factors that can cancel. We're also looking for common denominators when these are different, right? We can also get this in a common denominator. So this is going to be what? We have 2 and 3. So to get a greatest common denominator, that's going to be 2 times 3. And you can see there's just lots of different ways to do this. We have 3 times 6, which is 18 over 6 minus 2 over 6, which just becomes what? 16 over 6? But we can, those are both even, so we can get 8 over 3. Yeah, see, we can get to the same place. So we often have like a lot of roots if we know all of our fraction properties. So as we're doing these, I would definitely have like your fraction properties out and a piece of paper if you're doing these along with me. Okay. If we're writing things as a set, I picked out some important ones. If I say x is positive, what does it mean to be positive? Well, it just means to be bigger than 0. So x such that x is greater than 0 is how we would write this in set builder notation. Sorry, and that's what we're trying to do here, is we're trying to write these in set builder notation. T is less than 4. Well, it's exactly what it sounds. So we want all t such that t is less than 4. I also picked out E. This is an important one. The distance from P to 3 is at most 5. Oh, wait, I don't know if we're trying to do these in set builder notation. I think we may just be looking for this piece for these problems if you're looking at the book. But how do I formulate this into algebra? Well, the distance between two numbers, we need to think about the absolute value of subtraction. And if it's at most 5, then it has to be less than or equal to 5. This is how we would write E. Okay. Just wanted to do a quick couple of those. I don't think it's something we have to spend a lot of time on. If we're looking at the union of sets, we just want to make sure we include something if it's included in both of them. So for A union B, or if it's included in either one of them. So in A we have 1, 2, 3, 4, 5, 6, 7, and then in B we have 2, 4, 6, 8. Well, 2, 4, and 6 are already in A and they're in B, but 8 is in B but not in A. So we're just going to add 8 to A, and that's going to be our union. We just need to look at what's not in A but is in B. 1, 2, 3, 4, 5, 6, 7, and we get 8 as well because of B. What about the intersection? Well, we're looking for two things that are shared. Okay, excellent, Annie. Nice. Okay, so we have like 2 and 2, 4 and 4, and 6 and 6. And 8 is in B, but not in A. So for this one, we just have the overlap, right? That's the definition of the intersection is the overlap. So we have 2, 4, 6. Won't linger on this one. What if we have the intersection between two intervals? Okay, so we're going to go to our real number line, plot these out, and we were going to have what? We'll call this 2, we'll call this 6, we'll call this 10, and over here is, right, positive infinity this way and negative infinity this way. So we've got from 6 included everything over here. And we've got from 2 not included everything over here. But we're looking for the overlap since we're looking for the intersection. So it should be, well, we have everything that overlaps up to 2, but not including 2 because it's not including here. And we have everything up to 6 and including 6 because it's in both of these. So we should have 2, open bracket, not included, to 6 should be our result. These are exactly equal. Intersection is that. Okay. Okay. What do we do with like simplifying radical type problems? So for this one, it's important to remember that radicals distribute over division and multiplication. So the square root is going to distribute here, and we're going to get square root 4 over square root 9 equals, well, this is always the principal square root, so it's positive, so it should be 2 over 3. What about this one? Okay, we have a fourth root. Not as simple as this last one, but we're looking for one number that we can multiply 4 times and get 256. Well, okay, just using some reasoning skills. If I do 3 times 3, that's 9 times 3 is 27, times 3 is 81, so it's bigger than 3. If I do 4, and now I'm pulling out my calculator. 4 to the power 3, or sorry, 4 to the power 4. Okay, 4 to the power 4. I just tested that out. Don't know if you can see that with the glare. That is 256. Okay. Sweet. So I know what the fourth root of 256 is. It's 2. Because that's exactly what the root is asking by definition. Remember that the fourth root of 256 equals a is just asking what number a can I raise to the fourth to get 256. These are the same thing. Okay, what about the sixth root? Okay, well, remember that this is going to distribute again, so I'm going to get the sixth root of 1 and the sixth root of 64. And, well, usually we like whole numbers. If I take 1 to the 6th power, I just get 1. Okay, so I know what the top is. If I take 2 to the 6th power, well, that's like the second number whole number we can take to the 6th power, and that's 64. Okay. So this is exactly 1/2. And really the biggest property we're using is just that square roots distribute over division and multiplication. Okay, we want to simplify this. So we need to simplify the square roots. Remember that square roots break up over multiplication. So can we write 18 as like something with multiplication? Yes, we can. That's going to be 2 times 9. And then I remember that square roots break up over a multiplication, so I get square root of 2 times square root of 9, which is just square root of 2 times 3. And then over on the left-hand side, we can't neglect it. I can write this as a factor. I know this is divisible by 2, but then I get 16. So I can divide that by a 2 again, and I get 8, right? So 32 is end up going to be what? 2 to the 5th power, right? And that's just the same as 2 to the 4th times 2 to the 1st by the definition of the exponent, right? We just add exponents to multiply them together, so we can just break it up like it's addition, because that's, right, just 4 plus 1. So then we distribute, and we get square root of 2 to the 4 times the square root of 2. But I can simplify this as well, right? Because this is just the same as 2 squared squared. And that's going to cancel with the square root. So we're going to get 2 to the 2 squared times square root 2 plus square root 2 times 3. And this is just going to be 4. But notice that we can take the distributive property to get rid of this. So we're going to get 4 plus 3 times square root 2 by the distributive property. Why is the live stream blocked on school accounts? I'm guessing that's David. And I don't know. I will try and get it unblocked. Okay, so this is going to be 7 times square root 2. Ooh, okay. A lot of work. We just need to diligently apply our rules, right? Roots distribute over multiplication, so we're going to use our factoring knowledge about numbers. And we're going to do this when we do this with algebraic expressions, right? So everything we're doing with numbers, we're going to be doing with polynomials. Okay, and just like I said, okay, here's a polynomial. So we have square root of 16 times x. So that's going to be the same as square root of 16 times square root x plus, well, this is the same as x to the second times x to the second times x. I break those up into powers of 2 so I can get square root x to the second, square root x to the second times square root x. And then we're going to get 4, because this is 4 squared, times square root x. And this is going to become what? 4 times square root x plus x times square root x. And the same sort of deal, I notice a shared factor of square root x, so I can factor that out to get 4 plus x squared square root x. Okay. Okay, we got some exponent property stuff. So if I have z squared and z to the 4th up top, I'm going to use my definition of exponents to just combine those. And I'm going to get z to the 6th. And then on the bottom, I'm going to use the definition of exponent just to combine those. Multiplication becomes addition, so I get z squared. And then I can either use the reciprocal or know that division subtracts. I think it's just easy that division subtracts here, so I'm going to get z to the 4th, 6 minus 2. Okay, this one is practicing like a different rule for exponents. Exponents distribute over multiplication and division, just like roots do. So if I have a cube here, I can distribute because this is multiplication. So I'm going to get 2 cubed times y squared cubed. But power to a power, that's just multiplication. So I'm going to get 2 cubed, which is 8, times y to the 6th. 2 times 3. Okay, again, exponents distribute over multiplication, so I get 8 squared times x squared. I can't do anything else with the x squared, but I know what 8 squared is. It's 8 times 8, which is 64. Just diligently applying our rules and then moving forward. Right? We use the definition of exponents. We use the definition of exponents to simplify, and then we use the division property for exponents, right? Exponents turn multiplication into addition and division into subtraction. Okay. If you need more, let's just do some more. Okay. I'm gonna scroll down and I'm gonna do, I don't know, like 47A. And we're going to do the same sort of deal. If we see exponents over division or multiplication, we're going to distribute. And then we're going to add and subtract as we multiply and divide exponents. A to the 5th times a cubed. Being super careful to copy down the problem correctly if I want to check my work in the back of the book. Okay. Cubed. Okay. We have exponents over division. So I'm going to get a squared to the 5th power. And if I take exponent of an exponent, I just multiply. So I'm going to get a to the 10 and then b to the 5th. Then I'm going to multiply by and do the same thing. So exponents break up over division and multiplication. So I'm going to distribute this 3 to each individual piece because this is just division. and multiplication, right? So I'm going to get a cubed cubed, which if I think about a cubed cubed, that's a cubed times a cubed times a cubed, and clearly I can see that's 3 plus 3 plus 3, right? That's a to the 9. And then b squared cubed is b to the 6. Again, I have, right, 3 copies of this, and then c to the 9th. But then what I'm left with here is a fraction type of fraction, and I can just multiply those together and multiply straight across. So I'm going to get A10, A9, B6, B5, C9. We're going to use the definition of exponents to add those together, right? We're multiplying, so we add their exponents, 19, B, and then we have 6 here and B5. And this is all multiplication over multiplication, so I can subtract here and get B6 minus B5 to get B1. Well, that's just B. And then C9, I can't really do anything. And what do the instructions say? Simplify the expression and eliminate any negative exponents. Well, I don't see any negative exponents, so that is our solution. Okay, what about 47b? Okay, 47b, we're going to have u to the negative 1. Well, now we have a negative exponent. B squared all squared. And u cubed b to the negative 2 cubed. So what do we know about exponents? Well, when we have multiplication, we distribute. And then what do we know about exponentiating exponents? We multiply, power to a power rule. So we distribute and multiply. So distributing, we get, and multiplying, we get u to the negative 2. Negative 1 times 2. And then we get b to the 4, which is 2 times 2. On the bottom, same sort of deal. We get u to the 9, 3 times 3. And v to the negative 6. Okay. At this point, we have exponents over exponents, right? So if we have a negative exponent, we can change its sign and then just change it to the other side of the fraction. So we can take v6 up here and get v4 times v6 and take this down here to get u squared times u9. And then by the definition of exponents, b to the 10, 6 plus 4, u to the 11. And these are different variables, so we can't do nothing there. So we're not combining like terms because terms refers to addition. We are definitely simplifying and we're using the laws of exponents here. So from here to here, I use 2 laws of exponents. Exponents distribute over multiplication, and I multiply when I take powers to the powers, right? So AB to the power C is equal to AC BC. And also X to the Y to the power Z is equal to the X, Y times Z. By using these 2 properties, I get this first step. And then by using this property, X to the negative A equals 1 over X to the A, I can use that to flip these. So I'm just diligently applying the rules for exponents. So if you're struggling with the rules of exponents, I would take on these problems and have the properties of exponents out in front of you. Yeah. So if you don't know your exponent laws, right? Well, we're going to do another one, so let me just restate them here. A to the m times a to the n is equal to a to the m plus n. Multiplication becomes addition. That's like the definition. A to the m over a to the n, division becomes subtraction. A to the m times n equals a to the mn, and ab to the n equals an to the bn. Okay, and then a over b to the n is equal to an over bn, right? Distributes over multiplication, distributes over division. So that's how I kind of state those as one property. And then this is the definition. This is just, it turns division into subtraction. It's just like the definition. And then power to a power. So those are the rules of exponents. And then for everything else, I'm going to want to convert it into exponents and then use these properties because there's only 5 of them and they're kind of very straightforward. Distributes over multiplication, distributes over division, add them up when we multiply, subtract them when we divide. Okay. All that being said, let's do A. So, right? So if we're dividing, we can just subtract, right, by this property. So what's 3 minus negative 5, since these are both A? I'm going to get a 8. Well, actually, let's simplify the numeric part of this, right? We have multiplication and multiplication. So 8 over 2 is 4. So on the top, we're going to have 4. And then we're going to have a to the 3 plus 5. And then b to the negative 4 minus 5. And we're just using this property right here. So what we're going to be left with is 4a to the 8, b to the negative 9. But we don't want negative exponents, so we're going to turn this into 4a to the 8 over b to the 9. And what says we can do that? Oh, that's kind of like property 0. I wrote it on the other page, but a to the negative n equals 1 over a to the positive n. Okay, what about b? Well, we're just going to distribute, and we're going to get what? Y to the negative 3, 5 to the negative 3, x to the 2 to the negative 3. So what power of x am I going to have here? So 49b, I just want to make sure I wrote this down right. Annie, you still there? So this is the negative 2. So if I'm raised to the negative third power, what do I do with these two numbers when trying to get the power of x? Gonna get negative 2 times negative 3 is positive 6. And now we want to use these negative properties to flip these around. So this becomes 5 to the third over y to the third x to the sixth. And 5 to the third we can actually evaluate. That's 5 to the third is 125. y cubed x to the sixth. So we're going to want to keep these exponent properties in mind whenever we do something like this. Okay, so same sort of deal. We've got exponents. Let's just diligently apply the exponent properties. If I multiply these together, then I add them, and if I divide, I subtract. So this whole thing just becomes w 4 over 3 plus 2 over 3 minus 1 over 3. So I get 6 minus 1, which is w to the 5/3. What about this one? Okay, so we've got quite a little bit of a mess on top, so let's do that. So we're going to have s 5 over 2 times, well, let's do this power here. So we get 4 s to the 10 over 4. Or wait, we need to multiply by 2, right? So we're going to double the numerator, yeah. So then we want to get these both in terms of 4, right? Because we're going to add these. We've got s to the 1/2. So if I want to add these two together, because that's exponents, this is the same as 10 over 4. So I'm going to get s to the 20 over 4 times 4 over s to the 1/2, because we still haven't evaluated that yet. So 20 over 4, that's 5. And we get 4 s to the 5 minus the 1/2. So we're going to have 4 and s to the 4.5. Okay, whenever I have roots like this, I want to convert to its equivalent exponent and then do that. So I'm going to get y times y to the 1/2 all to the 1/3, which is going to get me what? Y to the 1/3 distributing the exponent, and then y to the third, 1/3 times 1/2 is y to the 1/6. Then we're going to add these together. 1/3 is the same as 2/6. So this is all going to be y to the 2/6 plus 1/6. Well, that's 1/2. That should be y to the 1/2. If I wanted to rewrite that as a radical, that's the same as square root of y. Okay. So let's look at b. I've got this radical. I'm going to rewrite it as a power. Or actually, before I even do that, I look at the inside and I see there's some stuff that I can cancel. So this is u1, this is v1. So v5 is the same as v4 times v1. So I can cancel one of the v's and I can cancel one of the u's to get what? The square root of 16 over u squared v to the 4th. And then notice that this whole thing is just a square, right? So we've got the square root, and this is 4, the u squared, over b squared squared. The whole thing is equal to the square root of 4u b squared squared. Square root cancels with the square, and we get 4u over v squared. Multiple ways to do this. Multiple ways to do this. Just keep following the rules. Okay. Skipping straight to page 42, we've got rational expressions like this. They're usually wanting us to factor here, to cancel some factors out. So x squared minus 4, hopefully we recognize that as a difference of squares. So that's x plus 2, x minus 2. And we've got x minus 2 and x minus 2 cancels. This is 1 over x plus 2. That's one of our quicker ones. As long as we see this factoring, right? A squared minus b squared equals a plus b, a minus b. Definitely need to know that one. Okay, this one, let's do some factoring and see if we can get some stuff to cancel out here. So looking at the top, I see a GCF of x. I'm going to take that out, x, and then I'm going to have x squared minus x minus 6. Now at the bottom, I don't have a GCF, so I'm going to have 2x squared minus 7x plus 6. Over here, I'm looking at two things that multiply to negative 6 and add up to negative 1. So if this is negative, then I need a positive and a negative factor, and they need to be a distance of, their absolute values need to be a distance of 1 away from each other, with the negative 1 being bigger. So what are two factors that are 1 away from each other that multiply to 6? That'd be 2 and 3. So let 3 be negative, and I get x to the x plus 2, x to the minus 3. And you can FOIL that out to confirm that is a correct factoring. This one's a little trickier, so I'm going to go up here just to my factor square, try and figure it out over here. So I've got 6, and I've got 2x squared, and I've got x. So I need it to add up to negative 7x here. So I need to use the factors of 3 or 6 again. So I can do negative 3, which gives me negative 6x, and negative 1, negative x. It may take you a few tries, right? I can just kind of see these because I'm doing it a lot, okay? So I've got a factoring of this right here because this adds up to negative 7x, positive 6, 2x squared. So I've expressed this thing as an area, which means I found my length and width equals length times width, right? So I have 2x minus 1 and x minus 3. I've got multiplication on the top and the bottom, and what do you know? I've got x minus 3 as a factor that canceled. It's almost like a human being wrote these problems to have nice stuff happen in our equations. That should be it. Okay. Nice. So you can always rely on a factor square and the trial and error method. Okay. Here we've got, hopefully you recognize immediately two difference of squares. This is already fully factored, so we don't have to worry about that. But let's worry about this because we could have some cross cancellation happening. Or maybe it's easier just to think of it this way, right? Multiply across, because that's what we do when we multiply fractions together. We get x squared minus 16, x minus 5. From a difference of squares, this is going to be x plus 5, x minus 5. 5 times 5 is 25, x times x is x squared, all checks out, x minus 4. Then I have another difference of squares, x plus 4, x minus 4, x minus 5. Now we've got multiplication on the top, multiplication on the bottom, and no like addition or subtraction in between, right? No terms. These are just factors. We can just cancel factors. Boom, boom. And we get x plus 5 over x plus 4. Okay, we have x plus 3 over 4x squared minus 9 divided by 6x squared minus x minus 2 over x plus 3. So we have division of a fraction, and I don't like this sign, but the book wrote it this way. Okay, so if we have division of a fraction, that's the same as multiplication by its reciprocal, x plus 3 over 6x squared minus x minus 2 times x plus 3, 4x squared minus 9. Okay, I see this, and I see a difference of squares. This is 2x squared and 3 squared. So I have x plus 3 over 2x minus 3, or sorry, 2x plus 3, 2x minus 3, doesn't really matter. X plus 3. And then over here, we can set up another factor square. 6x squared up in the top right corner, minus 2 in the bottom. So we could have x, x, and I guess 3 and 2. And I don't know. 1 and negative 2 are factors of 2. That gives us negative 4x, 3x, and does this add to negative x? Yes, it does. Okay. So over here, we get 3x minus 2, 2x plus 1. Okay, so it doesn't look like we have anything that cancels here. Nope. Okay. So we factored it. We're done. xy over z. Okay, well just remember that z is the same as z over 1. This is a fraction over a fraction. This is xy times the reciprocal, 1 over z. So we get x over yz. Done. Okay. Here's another one. Okay, I can write this over 1 and then multiply, but then I'm going to have a bunch of distributing to do. So instead, I'm going to look at the top and I'm going to get a like denominator, and then I'm going to subtract these from one another. So I'm going to do, what, x plus 1 times x minus 4 to get common denominator. Right, we just multiply. And then I want x plus 1 as a factor in the bottom over here. So x plus 1 times x plus 1. Nothing's changed. And we get, what, x plus 1 times x minus 3. Minus x plus 2 x minus 4 over x plus 1 times x minus 4, all divided by x plus 3 over 1. So now we can multiply by the reciprocal here. So just take this and multiply by x plus, or sorry, just multiply by 1 over x plus 3 And we just multiply through like we do with fractions. And on the top, we get, well, we can FOIL these out. So we get x squared minus 2x minus 3 minus x squared. Oh, yeah, we definitely should do this because the x squareds are going to cancel. And then we're going to get, yeah, x squared minus 2x minus 8 over x plus 1, x minus 4, x plus 3. Okay, so this cancels with, oh, this should be positive 2x because I need to distribute the negative over the whole thing after I FOIL. And before I apply the negative, this is going to be, yeah, x squared minus 2x minus 8. So I need to reverse the sign of each of these. Negative, positive, positive. Okay, that's important. So then we're going to get x squared cancels with negative x squared. 2x cancels with negative 2x cancels with 2x. And minus 3 plus 8 is 5 over, well, this mess. And I don't care to multiply it out. Besides, I think it looks neater in factored form. Okay, last one, we want to rewrite this. It actually says to rationalize the numerator. So how do we do that? Well, this is a numerator if you consider it's over 1. And then we multiply by the conjugate here. So the conjugate is we take this sum and we make whatever is negative positive and then multiply by that. So we're going to get square root of x squared plus 1 plus x over the square root of x squared plus 1 plus x. Okay, so this is a difference of squares. So on the top, we get this squared times this, which is just x squared plus 1, then minus x squared. Ooh, nice. Let's cancel. Then on the bottom, we have square root of x squared plus 1 plus x. Okay. And yeah, that will be it for the review, unless anyone else has any more questions. No problem. I hope it was helpful. I'm going to shut down the stream and go get dinner. I hope you get some rest too. And I will see you tomorrow, unless you're watching this later for review for the next test or something. Okay. Have a good night.